Hi, everyone. My name is Rayhan Azam. This project is called FALCON, which stands for Factual Aware Logical Consistency. The full title is FALCON, Factual Aware Logical Consistency for Large Language Model Outputs via NLI Guided Mixed Integer Optimization. At a high level, this project addresses a simple but important problem in natural language processing, which is that large language models often generate answers that are locally fluent but globally inconsistent. Because LLMs generate text autoaggressively, token by token, they can lose track of the overall logical consistency of a response. A model might make a claim in one sentence and then partially undermine or contradict that same claim a few sentences later. So even when the writing sounds polished, the reasoning may not actually hold together. This matters because many downstream applications depend on reliable multi-sentence reasoning. And as a result, my project asks whether we can enforce internal logical consistency after generation without retraining or fine-tuning the underlying language model. The core idea behind Falcon is to treat contradiction removal not just as a prompting trick, but as a structured post-processing optimization problem. Falcon has a pipeline that has four main stages. First, given a question, the base language model, which in my case was GPT-4o mini, it generates a raw answer. Second, that answer is broken into a set of candidate claims using rule-based extraction. In practice, I capped this at about 10 to 15 claims per response to keep the optimization computationally tractable. Third, for every pair of claims, I score how contradictory they are. And in order to do that, I use a pre-trained natural language inference model, specifically a DiBerta v3 cross-encoder. This gives me a weighted contradiction graph where claims are nodes and contradiction probabilities are edges. Finally, the fourth step is where Falcon really differs from simpler baselines, which is global optimization. I assign a binary decision variable to each claim and solve a mixed integer linear program to choose a globally compatible subset of claims. I evaluated two optimization settings. The first is hard mode and the second is soft mode. In hard mode, if two claims contradict each other above a chosen thresholds, they are not allowed to coexist. So the solver maximizes the value of the retained claims while enforcing an explicit incompatibility constraint. In soft mode, instead of strictly forbidding contradictions, we penalize them in the objective. This lets the solver balance contradiction removal against preserving useful information. After the solver selects the final subset of claims, those claims are passed back to the language model and rewritten into a coherent final response. That rewriting step is important because naive filtering alone often leaves behind fragmented or unnatural text. I compare Falcon against three baselines: raw generation, greedy filtering, and LLM self-reflection. The key distinction is that greedy filtering is local and can remove too much context, while self-reflection depends on the model identifying and fixing its own mistakes, which can be unreliable. Falcon instead makes an explicit, auditable mathematical decision over which claims can coexist. For my experiments, I evaluated on two data sets, strategy QA and truthful QA. Strategy QA requires implicit multi-step reasoning to produce a yes or no answer. It is a useful benchmark here because if consistency cleanup really helps, it should show up directly in exact match. Truthful QA is a bit different. It tests whether models mimic common human falsehoods in short explanatory answers. Since those answers are often open-ended, exact match is often too brittle, so overlap-based metrics become more informative. These two data sets let me test both a clean exact match setting and a more open-ended explanatory setting. Now, for the results, on strategy QA, raw generation achieves an exact match score of 0.30. Greedy filtering stays at 0.30 and self-reflection reaches 0.32. Falcon improves that to 0.40, which is the clearest headline result in the project. On truthful QA, exact match remains at 0 for all methods, which is not too surprising because exact match is a very harsh metric in that setting. But Falcon still improves the more informative overlap metrics. Token level F1 rises from 0.1665 to 0.2093, and Rogue L rises from 0.1526 to 0.1920. I also want to highlight an important ablation about the rewriting module. When I run the optimization but remove the final rewrite step, the strategy QA score drops to 0.34. That suggests the optimization alone is not enough. The best performance comes from combining contradiction-aware selection with semantic rewriting. Most importantly, across both data sets, Falcon reduces the measured contradiction count from a little over 2 contradictions per response down to 0. At the same time, I do recognize there are still limitations. The current claim extraction set is rule-based, so it can split semantic propositions somewhat awkwardly. A stronger future direction would be to use LLM-guided decomposition to generate cleaner claims. Also, because the contradiction signal comes from an NLI model, there is still some risk of evaluation circularity. So human-grounded evaluation would be an important next step. In conclusion, Falcon shows that you do not necessarily need to retrain a language model to improve its reasoning behavior. By framing internal logical consistency as a discrete global optimization problem, we can make model outputs more coherent, more auditable, and in some cases more accurate. Thank you very much for your time. Thank you for watching, and take care.